Hi, grade 7 learners. Welcome to Math Magic. Have fun and learn mathematics in a magical way. For this video, we will discuss about writing numbers in scientific notation and vice versa. Here are now our objectives. The learner will be able to first differentiate scientific notation and decimal notation. Second, write numbers in scientific notation and vice versa. Let's begin this lesson with a definition of significant figures. So when we talk about significant figures, these are digits that carry meaning in a number and contribute to its precision. Let me emphasize this class that identifying significant digits is very important in writing scientific notation. So first, you need to know how to identify significant figures or significant digits for you to understand how to write numbers in scientific notation. Here are now the rules in identifying significant digits. First, we have here all digits that are not zeros are significant. For example, we have here 2791. It has 4 significant digits. So we have here 1, 2, 3, 4. So we have 4 significant digits. Another 82.973. It has 5 significant digits. So we have here 1, 2, 3, 4, and 5. So it's very simple. When the digits are not zeros, then all the digits are considered as significant. Second, zeros may or may not be significant. Furthermore, number 1, zeros appearing between non-zero digits are significant. For example, so observe that 0 here, in this example 30.5, is in between 3 and 5. So in this case, 0 here is considered as significant. That is why in this number 30.5, it has 3 significant digits. So we have 1, 2, and 3. Another example is this one, 890,003. It has 6 significant digits since the zeros here are between 9 and 3. And 9 and 3 are non-zero digits. Another condition, zeros appearing in front of non-zero digits are not significant. So for example, we have here zeros to the left. So we have here 0.0013. The zeros in this example are located at the left of the non-zero digits. So meaning these zeros here are not significant. So meaning in this example, there are 2 significant digits. So we have 1 and 2. For the second example, still the zeros are to the left of the non-zero digit. So the non-zero digit here is 8. So meaning there is only 1 significant digit. Next, zeros at the end of the number and to the right of a decimal are significant. For example, we have here 15.0. So we have here zeros at the end of a number and to the right of a decimal are significant. So in this case, 0 here is located to the right of the decimal point. So here is now decimal point, and to the right of that is 0. So meaning this 0 here is considered as significant. So for this example, 15.0, it has 3 significant digits. We have 1, 2, and 3. For the second example, we have here 250,000.00. It has 8 significant digits. Since we have here the 2 zeros are located to the right of the decimal point. So we have here 1 and 2, 3, 4, 5, 6, 7, and 8. Next, zeros at the end of a number but to the left of the decimal point are not significant. So we have here 150. It has 2 significant digits. Since this 150, it's understood that there is a decimal point after 0, and that 0 is to the left of the decimal point. So this is not considered as significant. Therefore, 150 has 2 significant digits. Second example, 156,000. So it's understood we have decimal point after 0. So here, so to the left of the decimal point are the 3 zeros. So these zeros here are not significant. So therefore, we have only 3 significant digits, 1, 2, and 3. So 156,000 has 3 significant digits. Always remember the numbers that are not significant. So we have here zeros appearing in front of non-zero digits are not significant. So if it's appearing in front of the non-zero digits, these zeros are considered not significant. And if the zeros at the end of the number but to the left of the decimal point, we consider it as not significant. I think we're ready to discuss about scientific notation. Talking about scientific notation, it is a way of expressing numbers that are too large or too small to be conveniently written in decimal form. So take note of the words too large or too small. You say too large, for example, the distance between the Earth and the Sun. Of course, its distance is too large. So for our convenience, we can write it in scientific notation. For too small, we have objects or organisms that are too small. So we can also conveniently write it in scientific notation. So the scientific notation can be written in this form. Always remember this. The first factor A should be greater than or equal to 1 but less than 10. Please always remember this one. A should be greater than or equal to 1 but less than 10. What does it mean? When we talk about A, it should be greater than or equal to 1. So meaning your values could be 1 or more, but it should be less than 10. So your values could be 1, 2, 3, 4, 5, 6, 7, 8, and 9, or numbers between those numbers, but always remember it should not be equal to 10 or more. So it's okay when it's 9.4, 9.5, 9.9, 9.9995, as long as it will not reach to 10 or more. And then we have here, this 10 here is a constant, and this n here is the exponent. And the thing that you should also keep in mind in writing numbers in scientific notation is that you need to identify if it's a small number or a big or a large number. For small number, the exponent should be negative. When can we say that it is a small number? So we have here the following examples. Observe that for small numbers, the zeros are located in front of the non-zero digits. Okay? And notice that the ones place here is equal to 0. So not even 1, not even 2. So these numbers or these examples here are considered small numbers. And when you write it into a scientific notation, the exponent is negative. For large numbers, the exponent is positive. For example, we have here these numbers, 51 million. We have also 60 million. So these are examples of large numbers. And when you express it into scientific notation, its exponent is positive. Let's have this example. Change 345 million to scientific notation. We discussed a while ago that for small numbers, the exponent should be negative, and for large numbers, the exponent is positive. For this given 345 million, it can be classified under, of course, large number. For the scientific notation, it should be in the form a times 10 to the power of n. So our n here should be a positive number since 345 million is a very large number. So we have here 345 million, and it's understood that we have here a decimal point after 0 on this part. If we are going to convert it into its scientific notation, we will move to the left up until our first factor should be greater than or equal to 1 but less than 10. So I have here 1, 2, 3, 4, 5, 6, 7, 8. So we'll stop here because we already have 3.45. So always remember that we will write only the significant digits. So in this case, the significant digits here are 3, 4, and 5. So we'll write 3.45 times 10 is constant, and 8, we get 8 from the number of movements. That's 1, 2, 3, 4, 5, 6, 7, and 8. So we stop here. So that is 8. So it's positive because this is classified as a large number. Let's have more examples. How about this one? 0.000000189. Can we classify it as a large number or a small number? Of course, it is a small number. So, in writing it in scientific notation, it is equal to 1.89 times 10 to the power of negative 7. Why is it that this is now the answer, or this is now the scientific notation for this decimal form? So we have here the decimal point, and we'll find ways that our first factor should be equal to 1 or greater than 1 but less than 10. So we'll move to the right. 1, 2, 3, 4, 5, 6, 7. So we'll stop here. So that's 1.89. We'll write only the significant digits. And remember that numbers in front of the non-zero digits are not significant. So we have here 1.89 times 10 is constant. And where did we get negative 7? So we have here 1, 2, 3, 4, 5, 6, and 7. So it's the number of movements that is negative 7 since it is a very small number. Another example, 9,120,000,000. Is this a small number or a large number? Yes, it's a large number. So expect that your exponent should be positive. The scientific notation is equal to 9.12 times 10 to the power of 9. Where did we get 9.12? So we have here, it's understood that there is a decimal point here, and we'll move this one to the left. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we'll stop here because if we have 9.12, it satisfies the condition that our first factor should not be equal to or more than 10. It should be greater than or equal to 1, but less than 10. So this is 9.12 times 10. 10 is constant. And where did we get 9? From the number of movements. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9. Next example, 0.023. Is this a small number or a large number? Yes, it's a small number. So if we're going to write it in scientific notation, that is 2.3 times 10 to the power of negative 2. Where did we get these numbers here? So we have here decimal point. We'll move it to the right, 1 and 2. So we'll stop here because we already have 2.3, and 2.3 satisfies the condition where your first factor should be greater than or equal to 1, but less than 10. So that's 2.3 times 10. How about negative 2? So we have here 1 and 2, so that is negative. So it's negative because this is a small number. Let's have more examples. So always remember that for small numbers, the exponent is negative. For large numbers, the exponent is positive. And the scientific notation should be in the form a times 10 to the power of n, where your a should be greater than or equal to 1, but less than 10. And this 10 here is constant, and n is the exponent, or it's the number of movements. Let's have this example here. 75,512. So we have here, it's understood that the decimal point is after 2 or to the right of 2. So we'll find ways that our first factor should be greater than or equal to 1 but less than 10. So we'll move to the left 1, 2, 3, and 4. So we'll stop here. So we have 7.5512. So we have here the first factor, 7.5512. So it satisfies the condition that our a should not be equal to 10 or greater than 10. But it could be greater than 1 or equal to 1 times your 10 is constant and your n is the number of movements. So that is 1, 2, 3, 4. So it's positive 4 since 75,512 is classified as a large number. Second example, 804 million. So we have here, we'll find ways that our first factor is greater than or equal to 1 but less than 10. So we have here the decimal point is understood here. Then we'll move to the left. 1, 2, 3, 4, 5, 6, 7, and 8. We'll stop here so that our first factor is 8.04 times 10 to the power of 8. Why? Because we have here 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 movements, and it's positive since 804 million is a big number or a large number. Next, we have this example, 5.4. So we have here the first factor should be greater than or equal to 1 but less than 10. So we have here our decimal point. It already satisfies the condition. So no need to move the decimal point. So that is already 5.4, our first factor, times 10 to the power of 0 because there is no movement done. So that is 10 to the power of 0. Next, 0.000642. It is classified as a small number, so meaning our exponent later it's negative. So I'll find ways to satisfy the first factor. Our first factor should be greater than or equal to 1 but less than 10. So we'll move to the right. So 1, 2, 3, 4, and 5. We'll stop here because we already satisfied the condition. That's 6.42. 6.42, and we'll not write the zeros here because they are not significant. Times 10 is constant, and where did we get negative 5? That is 1, 2, 3, 4, and 5. And it's very small number, so that is negative. Next, 0.00000000843. So that is equal to 8.43 times 10 to the power of negative 10. So we have here, first, we'll find ways to satisfy the first factor, a, so it should be greater than or equal to 1 but less than 10. So we'll move to the left, out to the right rather. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we'll stop here. So we have here 8.43. It satisfies already the condition that our first factor should be greater than or equal to 1 but less than 10. Times, just copy the constant 10 and the number of movements, that's negative 10, since this is a very small number. What if the given is written in scientific notation and we're going to write it into its standard form or decimal notation? Always keep in mind that if the exponent is positive, you're going to add 0 or zeros to the right. And if the exponent is negative, you are going to add 0 or zeros to the left. For example, if we have 3.45 times 10 to the power of 8, so you have here the exponent is positive. What are you going to do is you're going to add zeros to the right. We have here The decimal point is here, so we'll move 1 and 2. So we have to move 8 places. So we have to add 6 zeros. So the equivalent standard notation of 3.45 times 10 to the power of 8 is equal to 345 million. So why is it equal to 345 million? So we have here, the point is here, so we'll move 1 and 2. So we have to have the target 8, so we have 3, 4, 5, 6, 7, 8. So that is 345 million. Another, 9.12 times 10 to the power of 9. So we have here, we'll move 1 and 2. So we need to add 7 zeros. So that is equal to, we have 1 and 2, 3, 4, 5, 6, 7, 8, and 9. So that is 9,120,000,000. Another example. So we have here 7.5512 times 10 to the power of 4. So same positive exponent. So we'll move to the right. So that is 1, 2, 3, and 4. So we'll stop. So the answer is 75,512. Another, 5.4 times 10 to the power of 0. How are we going to convert, or how are we going to write it into its decimal notation? So that is equal to 5.4, because the exponent here is 0, meaning there is no movement. So that is just equal to 5.4. For exponent which is negative, we need to add 0 or zeros to the left. For example, 6.42 times 10 to the power of negative 5. So our exponent here is negative. So our movement is going to the left. So we'll have here 1. So we have here 1, 2, 3, 4, and 5. So we'll put the decimal point here. So the equivalent decimal notation is 0.00000642. Another example, 8.43 times 10 to the power of negative 10. So we'll have here, we'll move going to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So then we'll put our decimal point here. So this is now the equivalent decimal notation or standard notation of 8.43 times 10 to the power of negative 10. Another, we'll have 1.89 times 10 to the power of negative 7. So we'll have here 1, 2, 3, 4, 5, 6, 7. So we'll have our decimal point here. And another, 2.3 times 10 to the power of negative 2. So our answer for this is, we'll have 1 and then 2. And then we'll put decimal point. So this is now the equivalent decimal notation for 2.3 times 10 to the power of negative 2. Thank you so much for watching. And don't forget to subscribe my YouTube channel. Bye-bye.